In this lesson, we will discuss configuring standard virtual switch policies. We will discuss the security properties of a virtual switch port group. They are security, traffic shaping, and NIC teaming policies. So there's three network policies that you can configure in a VMware vSphere environment. That is security, traffic shaping, and NIC teaming. The policies are defined by default at the virtual switch level. However, you can configure these at the port or port group level, and configuring any of these options at the port or port group level will override the defaults. It'll override anything set at the standard virtual switch level. So port or port group level configurations will override the switch level configurations. The first option is the security policy. You can see it there in the slide, the second tab that's actually highlighted there. If you go into the switch properties, right click and go to network properties, that will bring up the VM network properties dialog that we're seeing right there. And these are all layer 2 security options, and you can see the settings are promiscuous mode, MAC address changes, or forged transmits. And promiscuous mode, some of you may know, would be an option that if you had a network sniffing software that you wanted to see all of the traffic on a segment, not just the traffic that it was deemed for your particular virtual machine. You may want to see what else is going on out there and sniff that traffic. That would require promiscuous mode. And so you can set the virtual switch to prevent that from happening, to prevent an operating system from being able to put its adapter into promiscuous mode. Now, so what will happen is if an operating system does put its adapter into promiscuous mode, and you have this option set to reject, it'll just make that moot. It will not allow that traffic to be seen. That virtual machine will still only see its own traffic, or the traffic intended for it. It will essentially make that adapter not be allowed to go into promiscuous mode. If it's set to accept, then obviously it's just going to allow it to happen, and it'll see all the traffic that it would see on that segment there. MAC address changes, the second option, by default is set to accept, and if it's set to accept, it'll allow a guest to change the MAC address of the virtual network interface card. Now, if it's set to reject, and the guest decides to change its the MAC address of its virtual network interface card, then it'll just stop sending frames to that NIC, that virtual NIC. The last option is forged transmits, and by default that is set to accept as well. And if it's set to reject, then it will just drop the frames if a guest OS starts sending frames that have a MAC address that's different than that of the virtual NIC. So every virtual network interface card has a MAC address just like physical ones, and should that guest spoof its MAC address and send out a different source address, essentially saying I'm coming from a different MAC address, I'm not coming from the one you think I am, and this is set to reject, then it'll drop those frames. If it's set to accept, then it will allow it to forge the MAC address there. The next option is traffic shaping policy. Now, one thing I should point out, and you should remember, is that VMware traffic shaping only applies to outbound traffic. Should you desire to shape inbound traffic, then you would need to use an appliance. Again, it's outbound traffic only that this is applying to. And traffic shaping, as we'll see in a little bit here, has three different configurable options or parameters. Average rate, peak rate, and burst size are the configurable options, and it just allows you to control the bandwidth for a particular virtual machine. So to configure traffic shaping, it's disabled by default. So first thing is you would need to go into the tab there that we see on the bottom of the screen and actually enable the traffic shaping policy, and you'll see your three configuration options there: average bandwidth, peak bandwidth, and burst size. Average bandwidth is in kilobits per second, as well as is peak bandwidth, and the burst size is kilobytes, just straight kilobytes, not per second. And we'll see what the average bandwidth would be just every day. How much traffic are you allowing, or how fast? What's the speed that you're allowing to be transmitted out of this particular port? Now, peak would be, let's say that you would like to allow this particular guest to sometimes use more bandwidth. On average, you want it just to have a standard configuration, but then at certain times, maybe end of month or in the middle of the day, you want to allow it to actually use more bandwidth. Then you can set the peak bandwidth to greater than the average bandwidth, so it'll be allowed to use more. And it's not based on time of the day necessarily, but it would be for how long do you want to allow that burst to occur. And that's why the burst itself is a size. Let me give you an example here to work through this. Let's say that we set the traffic, the average bandwidth to be 500 megabits per second, and we set our peak to 1 gigabit per second. So on an average basis, this machine is only going to be allowed to use 500 megabits per second. Now, if it needs to burst and use more because maybe there's a large file transfer or something occurring, then we'll say, okay, you know what? Go ahead, you can use up to 1 gigabit per second. But how long are you going to allow this machine to use 1 gigabit per second? Well, that's what the burst rate or the burst defines, is how much data are you going to allow to transfer. So in this particular example, we're going to set that limit at 300 megabytes. Now, let's just do a little bit of quick math so we can make this easier to understand. 500 megabits per second translates into roughly 500,000 kilobits per second. The actual number's on the screen. 1 gigabit per second translates into roughly 1 million kilobits per second. And then 300 megabytes actually translates into about 2.5 million kilobits. And the math below that, just to kind of help if you're not following on this one, 1 megabyte is actually equal to just about 8,000 kilobits. Well, we have 300 megabytes, so 300 times that 8,000 kilobits gives us that 2,457,600 kilobits. And so if we wanted to burst up to 1 gigabit, and at 1 gigabit we were going to transfer 300 megabytes worth of data, if you do the math, that ends up being 2.5 seconds. So that 1 gigabit burst will run for 2.5 seconds, assuming it uses the entire 300 megabytes. The last option we'll discuss is NIC teaming policy. There's a bunch of different options here for NIC teaming as well. You can see that you can enable load balancing, again for outbound only, and we can also set the network failure detection, whether or not we want to notify switches upstream, the failback, and the failback order. Again, we'll dig into some more detail here in just a second. So let's start with load balancing. There's a couple different methods that vSphere can use to load balance. The first and easiest one is a load balancing method based on originating virtual port ID. Now, this is the virtual port ID of the virtual switch. In this particular case, every virtual machine is mapped to a particular physical network interface card. More specifically, every virtual network interface card, the virtual network interface card, is connected to or mapped to a physical network interface card. Now, what's good about this is that it requires no overhead. The port ID of the virtual switch, so whichever virtual NIC is connected to a port ID, that port ID that it is connected to is what determines which physical switch the traffic will be sent out. And so that doesn't require the VM kernel to actually do any sort of examination. It just sends it out. So let's see what that looks like. In this case, the first virtual machine sends out some traffic to the first host or to the first guest on the outside there, and you'll see that that is mapped to the first physical network interface card. The second virtual machine decides to send out some traffic, and so you'll see that it's connected to a different port on the virtual switch, and so it goes out a different physical network interface card. The third one decides it wants to send some traffic, again connected to a different virtual port ID on the switch, and so it goes out a different physical network adapter altogether. Now what happens when the fourth guy decides he wants to send? In this particular host, we only have 3 physical network adapter cards, so it just goes back up to the top, kind of cycles through them all, and balances out the load that way. Now in this particular situation, a virtual machine, any virtual machine that has only a single virtual network interface card will never be able to take advantage of more traffic than can be provided by a single physical network adapter card. That may have been a mouthful. Hopefully you'll understand what that means a little more as we look at the rest of the examples. The second way that we can do this is by mapping a virtual network interface card to a physical network interface card based on the MAC address of the virtual network interface card that's sending the data. This again, every virtual network interface card is mapped to a physical network interface card. So the first machine sends out some traffic based, again, this time now on the MAC address, not on the switch ID, but based on the MAC address of the virtual network interface card. It decides I'm going to send this traffic out this first physical network interface card. The second machine, having a different MAC address, the hash is created, and it decides to send out this traffic on a different network interface, a different physical network interface card. And so that's how this traffic is routed out through that second one there to that other host. Now, let's say the first virtual machine, the one that has the red path there, wants to send out traffic to a different host. Well, because again, the mapping is based on the source MAC address, so the virtual machine that's actually creating the traffic, it's based on the MAC address of that virtual network interface card. It goes out the same adapter that it went out before. Even though it's going to a different host or a different external guest, it's still going to go out the same physical network adapter card because that virtual NIC has the same MAC address. And like the other algorithm before, any virtual machine that has a single virtual network interface card can only use the total bandwidth of a single physical network interface card. In this next one, we'll see how we can actually take advantage of using the bandwidth of multiple physical network interface cards. The IP hash is the third method that VMware supports for load balancing. The way IP hash works is that the physical network adapter card that is chosen is based on the source and the destination IP address. And so the IP address from the virtual machine that's sending the traffic, as well as the IP address of the destination to which that traffic is intended to go. So between those two IP addresses, a hash is derived, and a physical network adapter card is chosen based on that hash. Now, obviously, this requires the VM kernel to evaluate the packets, look at the source and the destination IP addresses, and derive that hash. So a little bit higher CPU overhead for this particular method, but you'll see some of the advantages that we're able to gain as far as using multiple physical network adapter cards for a single virtual machine. So let's see what that looks like. The first virtual machine decides he wants to send traffic out over the network here to that first external guest there we see at the top right of the screen. And so it has the IP address of the VM, the source, and the IP address of that external guest, the destination IP address, and it decides based on those two that it's going to send traffic out that first physical network adapter card. Now, if the second guy decides to send out traffic, so the second virtual machine says, I want to send traffic to this external guest that happens to be this third one on the right. Again, two different IP addresses, a different hash, and so a different physical network adapter card that it sent out. Now, what happens if that first virtual machine decides that he wants to send traffic to yet another external guest? So the first VM wants to send some traffic to that second external guest on the right. Which network adapter card do you think we're going to go out? Well, in this case, because there's only 3 physical network adapter cards, we went out the third one. Now, why didn't it go out that first physical network adapter card, the same one that it sent traffic out for that red path there? Well, because, again, it's the same source IP address, but it's a different destination IP address. So that hash is going to be different because it's a different destination IP address. And so that's why we see that traffic go out that third physical network adapter card. So now we have a case where a single NIC, a single virtual network interface card machine, so a virtual machine that has a single network interface card, is actually, in this case, able to use the bandwidth from 2 different physical network interface cards. So maybe that hopefully makes a little more sense when I was talking earlier about the single NIC VMs can only use the bandwidth of a single physical adapter card in the previous 2 methods, because in either event, regardless of how the determination was made, the mapping was from a single virtual NIC to a single physical NIC. And in this example, we can see that a single virtual network interface card may actually map to more than 1 physical network adapter card, allowing you to take advantage of additional bandwidth. Now, to do this, there is a requirement upstream, and that is the support of LACP, or Ether channel. So Link Aggregation Control Protocol, LACP. That's 802.3AD. So 802.3AD needs to be supported on the upstream switch, or Ether channel if it's a Cisco switch. That's Cisco's version of LACP. And so if you have that, you can take advantage of this type of NIC teaming. And what the Link Aggregation Control Protocol allows you to do is group several physical network interface links, several physical Ethernet links, into one logical Ethernet link. And so it takes those multiple links, makes them look like one, and that allows us to do things such as fault tolerance and also for increased bandwidth. But again, you have to have that support upstream in the physical switch to actually allow that to take advantage of those protocols. Now, when a virtual machine communicates with the outside world to different clients or different machines externally, the traffic, as we're seeing in this particular example, may go out different network interface cards. And again, this is only outbound traffic that it can control. So that traffic from those clients may very well come in on different adapters altogether, and thus the need for the Ether channel or LACP protocol being supported. And so under the NIC teaming tab, there are several different options in there. What we talked about so far was load balancing, but then you'll see there's also network failure detection, notify switches, failback, and fail over order. Now, what that is under the network failure detection, there's 2 different options in there. There's link state and there's link state plus beaconing. Now, if you have network failure detection enabled, that's going to give us the fault tolerance that we're looking for. If you have that enabled, you can choose one of 2 options. Link state only will do just that. It will only look at the state of the link on the physical network adapter card itself. So if a cable is pulled, if something is disconnected between the host and the virtual machine that's upstream, then it'll detect a failure. Now, if something happens upstream from that switch, so between the switch that the virtual machine is connected to and this, a router or switch that's above that, if something becomes disconnected there, and that results in the virtual machine not having access to the rest of the network, link only or link state only will not detect that, because if the cable between the host and that physical switch, the first physical switch, is in proper working order, then you're obviously not going to, it's not going to look like there's an issue, but yet you may not have access to the network. And that's when beaconing comes in. So link state plus beaconing will check that link state, but then also will send out a beacon of 62 bytes, a packet of 62 bytes, every so often to actually check and see if there's a response upstream to see if there's actual connection. Now, the switches that are upstream obviously have to support beaconing, otherwise that's not an option. And as I mentioned, there's a little bit of an overhead there with beaconing because there is that 62 byte packet that's sent out periodically. So when a detection is, or when a failure is detected, what should we do? And that's what the notify switches option is going to determine. What should we tell the rest of the network? Should we tell the switch upstream that an issue has occurred? Now, why would we want to do that? Well, the switches should be able to adjust their routing tables and recover from a failure, but there may be some latency there. So if we tell the host that it should notify the switch upstream that there's an issue, that'll allow those switches to update their route tables, and that'll reduce the latency in getting that traffic to route appropriately back to that virtual machine. The last option is fallback. When a switch is, or when a physical network adapter card is repaired, what do you want to do? So if I have two physical network adapter cards and I have failover enabled, or I have network failover detection, failure detection enabled, and I have it set up so that when one of my physical network cards goes out, or a link upstream from it goes bad, then I'll fail over to the other adapter to ensure that my network is up and running. What happens when I repair that primary connection? So we failed over to the secondary, everything's up and running, we have network traffic flowing, but the admin then comes in and fixes whatever that initial issue was. So now that primary adapter is back online. What do you want the host to do? If you have failback set to yes, then the adapter is immediately placed back into service. If failback is set to no, then the primary adapter, which was the primary adapter, the one that experienced the failure, will go into standby mode, and the adapter that you're currently failed over to, which was the secondary, will now become your primary, and you'll just remain on that new adapter until such time that it should fail, and you may need to fail back over to the secondary. The last option actually is the failover order, and if you go in there, you can override the order in which the failover occurs if you have more than one or more than two, I guess, physical network adapters, and which ones you want to actually specify as the secondary or tertiary adapters.